Yes, in the last video we concluded by seeing that when we have a random variable, we can assign certain events to this random variable. For example, such events as x equals any number, or x is less than or equal to any number. This is then an event to which we can assign a probability, and we want to use this now we will get to know the concept of distribution. We will first do this for so-called discrete random variables, and then in the second part, in the next video, we will deal with continuous random variables. So let's first consider what it actually means for a random variable to be discrete. And that means a random variable is a function. And we can ask how many values does this function take? And if these are only finite, that would be one possibility. So that is also the part we primarily consider, or they can take on countably infinite values. If you are interested, we will take another look at this in the lecture. You can imagine that if you know about countable and finite values, then just think of a finite number of values that can be taken in contrast to continuously many values. So, for example, all values between 0 and 1 would be the opposite. Exactly. And countable means that we can essentially write it down in a list. You can imagine it like that. And if we have a discrete random variable, meaning only these countable or finite values that we can write in a list, then we can look at the event x equals this value. We have learned that this is an event, and to this event we can assign a probability. So this would be this part here, and we then call this probability pi. A probability distribution is simply that we take the so-called realizations, meaning the values together with these probabilities, pi, which together form the distribution. And the simplest way to represent such a distribution is through a table. We will look at that in the next step. So we basically want to look at the probability distribution for the double dice throw, and exactly for that we have our omega again, which consists of these tuples. And we have also seen that omega d consists of 36 elements. And we have our random variable x, which is nothing other than the sum of the two numbers. And now we need to determine the probability distribution of this random experiment. And for that, let's first consider what a continuous or discrete random variable actually is. So, what are the values of x? And the values are, of course, all possible sums. And that means, so x1 is equal to 2, x2 is equal to 3, x4 is equal to 4, and so on, up to x11 is equal to 12. So these are all possible values. There are finitely many, so it is a discrete random variable. And what we need to do now are the pi's. So we need to consider what the probability is. Let's start briefly with the case where x equals 2. That would be our P1. And how do we do that? We need to consider that this is a Laplace experiment in the sense that each of these tuples here is equally likely. So we need to count the possible tuples that result in a sum of 2, and there is only one tuple that does this, namely the tuple 1.1. This means we have 1 out of 36. And what we can do now is we can create a table here that says on one side we have the xi's and on the other side we have the pi's. And if xi equals 2, then we have a 36. And When we fill out this table now, then it is nothing other than that we have determined the distribution of this random variable. Let's do a second example, P2. So P of x is equal to 3. So we need to consider again how many ways there are to have the outcome of 3. And there are two possibilities. 1 and 2, 2 and 1, so 2.36. That means if we have 3 here as a realization, we have 2.36 here, and you should think about it yourself. For the 4, we actually have 3 possibilities. For the 5, we will have 4 possibilities. For the 6, we have 5 possibilities, and for the 7, we have 6 possibilities. And, right, the 8, now we have the 8, the 9, the 10, the 11, and the 12. And if we start again from the right, then the 12 also has only one possibility, namely 6 and 6. That means this is also a 36 here. Then you see that the game goes the same way from the other side, until we then arrive exactly at 7. And what you see is that the sum of the dice 7 is therefore the most likely sum of the dice with 7.36. You can theoretically calculate it again now. Feel free to do that once more. Pause for a moment and consider whether the sum of these values here actually equals 1. Just notice that I have here. I just realized that I forgot a 36 here, so that the sum of all these values actually equals 1. And if we wanted to plot this as a bar chart, it would look like this, symmetric around the sum of 7. The sum of 7 is the highest point, while 2 and 12 have the lowest probability, respectively. Can you also think about why that is the case? Note, you can simply flip the dice to the other side. If you turn both dice over once, you will get exactly the mirrored result. And I think that is a good indication of why everything is symmetrical. Yes, that is the probability distribution, and what we can define now is a so-called distribution function. So what we can do now is define another function alongside the random variable that includes the following. Namely, it asks itself, I will mark this here, this is f, and this is the probability that the sum of the dice is less than or equal to a specific value. And we also call this the distribution function, or sometimes the cumulative distribution function. And what you can already see here is that if we increase the values of x, then of course the probability that the sum of the dice is less than this value will also increase. And what you can also see is that the values of x can be real numbers. In our case, this only makes a difference if I have whole numbers, because I can only roll whole numbers. That means the distribution function looks like this. So it is a step function, where we need to think a bit about what exactly happens at these steps. And you might want to think about that, for example, with the 4. Is it now the value, or is it the value? And indeed, think about it for a moment. It is actually this value here at this point, because we have a small equal situation. This means that the probability of rolling a 4 is, so to speak, included. And that means sometimes you can also do it this way, that you have here a draw a hollow circle and then also draw a filled circle here. Good. And what you can also see, of course, is that if you go very far back, the probability is 0, up to that value, which is actually not included. But if we were to go even further, then the probability here would be 0, and only at 2 does it start to increase. That means when the value is particularly small, this distribution function is always 0, and when the value is particularly large, well, then the probability must eventually be 1. This is the case here, so to speak, because the probability that the sum of 2 dice is greater than 100 or less than or equal to 100 is, of course, 1, because the maximum is 12. At some point I exceed this maximum that can result from the values and eventually obtain the value 1 for the distribution function. And now finally, we want to take a look at a sentence about the distribution function that is relatively practical in nature, namely a few properties of this function. So first of all, it grows monotonically, of course. At the beginning it is 0, then it is 1. We have just looked at that, because at some point, so to speak, the value can no longer increase, and then the probability must be 1. This means that the following holds. All right, let's move on. At each point, there exists a right-hand and a left-hand limit of the distribution. However, it does not have to be identical. At the jump points, it is of course not identical. And we can take a look at that here as well. So, if the notation is unfamiliar to you, that's not a problem. It's not so bad. But for those who are familiar with it, let's take a look. First, the left-hand limit. This is almost the value at this point, so f of x0. Only, we do not have an equality sign here. So it is, so to speak, the value for less than x0, and from the other side, it is the value less than or equal to x0. That is new. Yes, so to speak, we can also take another look here. That, when we come from the left, the value is, so to speak, the lower one. And when we come from the right side, the value here is the upper one. And this value here would therefore be smaller. So that would be smaller here. And that would be less than or equal to at this point. Okay, and that also means, and this is quite an exciting thing, that when we have a jump point, the question arises, what does the height of the jump mean? And that is simply the probability that exactly this value occurs. So to speak, the jump height is nothing other than the probability that exactly x equals x0 occurs. In other words, if we take the limit from one side minus the limit from the other side, then we have p of x less than or equal to x0 minus p of x less than x0. And that is exactly this value that is assumed. This means that the jump points are, so to speak, just as large as the bars we saw earlier in the distribution function. Yes, that was essentially what I wanted to explain to you about the concept of randomness. That is, distribution and distribution function. In the next step, we want to look at how to do this for continuous random variables, meaning random variables that can take on not just a finite or countably infinite number of values, but any continuous values. A typical random variable would be a person's height, which is continuously variable. And that's a bit more complicated as we need the concept of a density, and then we will need integrals, but more on that in the next video.